When we first defined derivatives, one of our initial tasks was to go through and prove as many differentiation rules as we could. For example, we would prove what the derivative of a power was, we'd prove what the derivative of the sum of two things was, and so on. Then when it came time to do integration, we've already seen how to do the integral, for instance, of x to the n a power. We've seen how rules like that the derivative of a sum is the sum of the derivatives carry over into the integration context, and indeed that the integral of a sum is the sum of the different integrals. Now, one rule from differentiation that we haven't dealt with yet in the integration context is the chain rule. So here I've put it up for you. It's the derivative of like a composition, an outside function big F, a little function g was the derivative of the outside at the inside finally multiplied by the derivative of the inside. And note, by the way, as I set up this formula in its standard form, I'm using a capital F on the outside and a little g here. And indeed, whenever we're doing integration, we will typically adopt that the derivative of big F is little f. Or in other words, big F is the antiderivative of little f. So let me take that little notation and fire that into the formula here. So in other words, I'm going to say d dx of big F of g of x is little f at g of x times g prime of x. Now, this is just an equation in terms of the variable x. We have this function of x on the left and this other function of x on the right. So I can take the integral of both sides with respect to x. So let me wrap this in integral signs. I'm saying the integral with respect to x, that's what the dx means, integral with respect to x of the derivative with respect to x of big F of g of x, and that's going to be equal to the integral also with respect to x of f of g of x times g prime of x. Now, the left-hand side, I know how to deal with this because when I'm asking for the indefinite integral of something, I want to be able to find some antiderivative, and I know that the general form here is that antiderivative plus an arbitrary constant c. So the question is, what is an antiderivative to this inside function? Well, an antiderivative to the derivative of something is just that something. So in other words, this left-hand side here is just going to be f of g of x plus c, and I copy and paste the right-hand side, where this f of g of x is going to be an antiderivative of the derivative of f of g of x. So what I have in effect done is I've derived this particular equation, which is a way of computing out what the integral of this funky form, somewhat bizarre form, f of g times g prime, but if we have an integral of that form, we can figure out what its antiderivative is as long as we know what the antiderivative of just the f is going to be. And indeed, this is going to substantially widen for us the class of functions that we're able to integrate. This equation that we have is typically called the substitution rule. And indeed, while it's perfectly fine written as it is, we can often simplify it, at least notationally, and we call it something called U substitution. And the idea for U substitution is just to give a fancy name here. So what I'm going to do is this g of x, which is a little large, I'm going to simplify and just call it U. Then if I take this left-hand side and I try to make it equal to something, I'm saying, so the g of x was u, so I just say it's f of u plus c. Now, big F of u of plus c, I can write that as an integral because big F represents an antiderivative to little f. So I can take this f of u plus c and I can write it as the integral of f of u du. Note, by the way, that we've often written things the integral of f of x dx, but it doesn't matter what we call a variable. It can be f of u du, f of t dt, f of g dg. It really doesn't matter. We conventionally use for u substitution f of u du. So what we've really compared here is we've taken this integral of f of g times g prime dx, and we've written it just as, by this substitution with u equals g of x, as f of u du. So then finally, if I compare these two expressions that we have here, the f of g of x, when I plug in u, is just f of u, which is what I have down here. And so what remains, the g prime of x dx, I can identify that with just this du. So in other words, I'm saying that the du is going to be this g prime of x dx. I'm going to finally summarize it as saying this substitution rule is going to allow us to take integrals of this funky type, By letting u equals the g of x, we can rewrite this as the integral of f of u du, and we get its answer. It's just going to be f of u plus c. Okay, so let's see how it works out in a specific example. Here I have the integral of 2x times sine of x squared dx. Now, my first task is to take this integral and try to write it in this nice format. I want to identify what should be my f, what should be my u, and what should be my du. So first thing I'm going to do is I'm going to sort of try to color code a little bit. You notice how there's a sine of x squared? So you think there's an outer function sine and an inner function x squared. We have that composition. And then the derivative of x squared is 2x. And notice that I have combined this 2x dx. So I'm going to set that my u is equal to x squared. I'm going to set my du is equal to the 2x dx. My function is going to be this sine of u, and its antiderivative, I know the antiderivative to sine is going to be minus cosine of u. So I've sort of gone off on the side here and I've collected all the relevant pieces of information. So it now looks like something of this form. And so what I'm going to do is now plug into the answer. It's the antiderivative of f of u. Well, the antiderivative is right here. It's the minus cos of u. U is x squared. And so what we're going to finally get is that this is equal to minus cos of x squared, and then finally plus the all-important c.